Um, when I was preparing this presentation, this book helped me a lot, Deciphering Data Architectures by James Serra. It was published this year. It's very new, and if you want to dive deep into the topic of data engineering, this is a pretty good place to start. Agenda. We will talk today about a relational data warehouse, the classics that has been around for decades. Then data lake, the so-called modern data warehouse, the data fabric, data lakehouse, data mesh, and then in the end we will have a demo. Let's begin. What is a relational data warehouse? It is a classical solution that has been used by different business entities for many years by now. It is a relational data database that is aggregating data from different parts of a big business and presenting it as a single point of truth for different reporting solutions, for data science. Usually it has a star or snowflake schema, and it allows to remove the stress from production system. When we have a production database that is responsible for sales, for example, or for recording some kind of events, then we don't really want to run reporting on this database because it is under enough stress already. So we use data warehouse. And this model was working fine for many years. And of course, the natural question is, what's wrong with it? Why do we need something else? The biggest issue with a relational data warehouse is the data need to be prepared before it is, they can be added to relational data warehouse. If, for example, a company opens new kind of business or decide to include another area into data warehouse, it will take time, sometimes quite a lot of time, to design the additional structure, to build ETL pipelines. And during that time, this data will not be available for reports, for data science. Sometimes this gap is unacceptable. Business wants to use the new data immediately. That's why new and more modern approach to architecture has been developed. There are two approaches to getting our value out of data. The so-called top-down deductive approach and bottom-up inductive approach. In the top-down approach, we know what kind of question we are asking. We have a theory, we want to prove that theory or disprove. With bottoms-up approach, we just have the data. We don't know what to ask. We want to look and see what kind of insight the data can provide by itself. The top-down approach is the one that is used in traditional relational data warehouse. The bottoms-up is the more modern, and it is used in systems like data lake and lakehouse. Yes, as I said, relational data warehouse uses a top-down approach. So first, we take a strategy, we gather requirements, we, based on this requirement, we build architecture, we build ETL, infrastructure, we get the result. The data lakes is using a bottoms-up approach. We take a bunch of data, put it all together, and then we think what can we get from it? What insight this data can give us when we analyze it all at once? The best approach is to use both for different kind of tasks, for different kind of problems. And that is exactly what the so-called modern data warehouse is trying to do. First, a few words about what is data lake. Data lake is, at its heart, basically a lot of files put together. It can be any kind of files. It can be Excel tables. It can be video, audio recordings, all sorts of feeds, reports, text descriptions, and so on. Unstructured. The most important word about this data, it is unstructured, unlike the relational data. And of course, when it's just lying there in data lake, it doesn't provide a lot of value. We need some kind of engine to look at this data, to process it and analyze. Why do we want to use a data lake? Because it does not take any time to save file in a folder, usually somewhere in the cloud. It will take time then to analyze it, but to add something to the data lake, it's immediate. There is no waiting in the middle. And if users know how to, by users, I mean not the end users who will be looking at the report, but people who are building reports or data scientists who build data science models, if they know already how to work with different unstructured data in data lake, they can do so immediately. When data is stored in data lake in the cloud, you can use parallel processing systems to process it very fast. Because relational database, sometimes the processing power becomes a bottleneck. With data lake, it's not, because if we have a problem with processing, we just can add more and more nodes to the cluster and run the same code in parallel on more virtual machines. So how modern data warehouse include both approaches, how it tries to be the best of both worlds. In the high-level overview, first, when we get data from data sources and ingest it into the storage, this is the same as it was with relational data warehouse. It is stored, the data is stored in data lake, and at this point, without waiting for transformation of this data into the relational model, data scientists can already start working with it. Because data scientists usually know how to use programming languages such as Python or Scala to process the raw unstructured data, and sometimes they even prefer to do that. It gives them more information than a refined version of the data already in the final storage. Then we do the transform. Here we use this cloud-based clusters of virtual machines to process it, to do the massive parallel processing of this data without putting any sort of pressure on a relational database. And then we have the model, and this is our familiar relational data warehouse, something that we've been using before. But here it's not the whole system, it's just the end of the line. Because processing is no longer done inside of relational data warehouse. Storage of raw data is no longer done inside of relational data warehouse. It's decoupled, and every part of this system does what it can do best. Data lake and data warehouse have different use cases. In data lake, Data scientists like to use with raw data when with data warehouse reporting systems. Oh, look, a cat. Yes. Data warehouse has its own advantages because for complex SQL queries, which involve a lot of joins, but not too much aggregation, relational data warehouse can be faster, while if we do a lot of aggregation on a massive amount of data, a data lake will get us better performance. Data warehouse, relational data warehouse will usually have better security, things like row level security, column level security, while with data lake, you either have access to the whole file or you don't. If we look at the diagram of modern data warehouse architecture, it shows us pretty much the same picture, but with a little more details. We can ingest different types of sources, be it relational databases, structured or unstructured or semi-structured files. They are stored and transformed in data lake, then saved into the relational data warehouse storage. This approach helps us to avoid maintenance windows in relational data warehouse. It is a pretty common practice, at least it was with the older architecture, that new data is loaded into data warehouse, and then the processing and aggregating begins, and during this process, it typically happens in the middle of the night, the whole data warehouse is not available because it's busy, it's calculating. With this approach, it's no longer the case. This part is busy, this part is working, and then the transformation of aggregated data happens very fast. There is no delay. Data fabric is an evolution of idea of the modern data warehouse. It uses a very similar approach, a lot of the same structural elements, but it adds a layer of metadata on top. So from the outsider perspective, if I am a reporting system and I'm looking at this whole structure, I don't want to know what is data lake, what is not, like all the internal components of it. I want to see a clear API, and I don't want to know what's inside. This idea is implemented by the data fabric. Once again, it is using relational data warehouse as the model. Once again, it is using data lake as a storage and transformation tool, but it adds the layer of metadata, API, and advanced security to improve the process of communication between data warehouse and the outside world. It also can add things like metadata catalog to list all the data that is available, so the search would be made easier. Sometimes it involves master data management systems and so on. So it is built from the same building blocks. It's just an evolution, the next logical step. If we look at the architectural diagram, you will see that it is very similar to what we've seen before. It adds the metadata component and it adds the API component. But the rest is the same as with the modern data warehouse. By the way, I don't really like this name, modern data warehouse, because how long will it stay modern? But I haven't seen a better term for it, so if you know one, please tell me. And then we come to the idea of data lakehouse. If data fabric was an evolution of previous idea, this is a revolution. because it changes the core concept. It removes relational database entirely. It only operates with files. It stores the files in data lake, it processes the files in data lake, and it also offers these files to external systems like reporting tools as files with a layer of metadata on top. It is based on the technologies such as delta table. Delta is a format of a file based on a format called Parquet. And the idea is it is a file with transactional log. You can take a file and you can do operations such as insert, update, and delete on the data inside. And all changes that you do will be reflected in transactional log. It's still a file, but it operates very much like a database. It is optimized for queries and aggregations. And since it's a file, it can be processed in a massive parallel processing way by a cluster of compute. So again, we do not see these problems that we saw with relational data warehouse when calculations were a bottleneck. Since we have a transactional log, we can do things like time travel to see what were the previous versions of the same data before some kind of transactions that was happening. And to avoid unlimited growth of transactional log, the delta format offers us some operations to shrink log, to remove the history if it's no longer relevant. This idea was very big when it first appeared because removing relational component entirely allowed to go away from relatively expensive and sometimes slow database systems to completely open source world. Of course, it's no longer entirely open source. There are a lot of commercial products in that area, but it started as an open source. In the high-level architecture, you can see that there are some similarities with what we see, what we've seen before, but the model, it's no longer relational. It imitates the relational database by providing a layer of metadata, but really it's just files in a lake. According to reporting systems, when they look at it, they see relational structures. They see tables, they see rows in those tables, columns, everything they are used to. But really, it's not there. It's just the metadata and files. The old school relational data warehouses suffers from several problems. The data in the source and the processed aggregated data in data warehouse could get out of sync if because we don't do the processing and aggregation very often. Usually, well, quite often, at least it was once a day. And during the day, this gap could grow. In this case, it's no longer the issue because there is no pre- and post-aggregated data. There is just one data in data lake. So it's pretty much almost real time. The extra cost could be added by the process of moving data between source and the relational data warehouse. It's no longer the case. It's not copied. It's just one copy of the data, the files in data lake. The security aspect, because there is less copies, less places where it could be exposed. The last one is complexity. More specialized skills needed for both data lake and relational data warehouse. Well, that is not 100% true. I mean, this problem existed for relational data warehouse, but it still exists for data lakehouse because it adds its own complexity. So I can't say that it has become much easier to work with data lakehouse than to work with relational data warehouse. But other advantages still there, and they're still quite important. So for data lakehouse architecture, you can see that we get the data from the source, we store it in data lake, we process it in data lake, and then we present it to the outside world through the layer of relational metadata. So this is not really a database. It's metadata that imitates a database. And the users don't need to worry. Is it real database? Is it metadata? They see their tables, they can query them, and it just works. There are, though, several concerns if we decide to remove relational component. The first one is speed. When we are aggregating huge amount of data, the data lake approach will work faster. But when we just want to query one table with some kind of simple select, relational database will still be faster because of the built-in caching mechanisms. And in case of Delta Lake, we have just read file from the disk. It always will take time. So if you need this kind of split-second read operations from your data warehouse, then you probably still need the relational layer in it. Also, this kind of metadata is not perfect in terms of security. It currently does not support row-level security or column-level security and other important security requirements. It is evolving. And I believe that in the near future, those kind of gaps will be covered, but right now they are still not. There are some other issues related to skipping relational database. I would say they are less serious than the ones that I named, but still, when making this kind of decisions, you must remember about them and you must discuss with the business if they are ready for that kind of sacrifice or not. Data mesh. It is a different approach to data architecture, but I cannot say that it is a revolution. It is rather trying to answer the question what to do if data architecture grows too big. If we have a huge corporation with multiple departments, with multiple data owners who find it difficult to synchronize everything between them just because of the size of the complexity of the whole big system, then maybe data mesh would be an answer. The data mesh is a system when there is no central storage. Every specific department, every specific owner of the data provides their own interface to operate with their data, and only on high level, on metadata level, it is all united into a single system. And important thing to remember about it is data mesh is more a concept than a technology. It is an organizational shift. You need to, when you're implementing data mesh, it's not as much about installing and setting up a new software. It's mostly about changing the corporate structure and setting up correct people in correct places to make this kind of system possible. And since it's a organizational change, it is usually very slow and very expensive. So it is, I would say, it's the last solution if nothing else helps. It is a domain-oriented, decentralized data ownership and architecture system when every domain is treating their own data as their own little data warehouse, and the domain is directly responsible for the quality of their data, for the availability of their data, and so on. For every domain, data is treated as a product. Sorry. There is no central storage and no central team of data engineers who are responsible for everything. Each domain has their own data engineers who are supporting their own part of data mesh, who knows their own data and can better work with it than someone who cannot, of course, keep in one head data related to 100 domains. This diagram is from the Google version of data mesh because they have better diagrams, in my opinion, but the similar things exist in Azure and Amazon Cloud. In this diagram, you see different data domains, like this one, and each of them have their own storage and their own API to provide their data for an outside world. And a system that unites all of that, that creates one big structure out of all of that, it's just the metadata. The actual data stays where it is. It belongs to domains. And when someone wants to query it, they will have to query it from the storage in inside of a specific domain. And if there is a problem with the data, then a specific domain is responsible to solving it. In a very big organizations, there is sometimes a problem of lack of ownership because the data source team doesn't know all about data from every domain, cannot effectively fix or even find problems with it, controls the quality, and solve every issue. The data mesh approach is supposed to fix that and provide a solution when every domain owns their own data and more effectively can control it. There are, of course, concerns with data mesh. The biggest concern is that it is very new. And as far as I know, there is no success stories yet with it. Because even companies that decided to accept this model and go with it, it takes so long to build this organizational structure, to change everything and prepare for using data mesh that no one, at least not to public knowledge, has successfully finished it yet. There is no standard for data mesh. There are a lot of different understandings how it is supposed to work, what it's supposed to look like, and when you are trying to implement data mesh, you can never be exactly sure what is expected, like what it will look like. Organizational change means huge investment. And for business people, the question, of course, arrives, will this investment pay off? Will the result be worth it? And right now, it is very difficult to say yes with any amount of certainty. Because, as I said, there are very few success stories, or even none. Every domain that will be responsible for their own data need competent data engineers and data stewards to control the quality of their data and to resolve issues with it. It means a lot of additional personnel. Sometimes it's hard to find, sometimes it's expensive to keep. It's, of course, a business concern more than technical concern, but we must keep it in mind. And there are some other things too. So as I mentioned before, in my opinion, data mesh is the last solution if nothing else helped. But this concept exists. It is getting some popularity over time, and who knows, maybe in a few years it will be the next standard, so to speak, but not yet. And now I would say, most important slide, when to use each architecture. Because this presentation is called choosing between architectures, so how do we choose? And the correct answer is, as always, it depends. Because there are so many factors that you must remember, that you must take into consideration when you make this sort of decision. This list that I provided here can be used just as a basis, but not as a criteria to make this sort of decision. There are huge amounts of factors that needs to be taken into account. But yet, it can be used for a raw estimation, so let's go through it. Modern data warehouse can be used if the company, the client can't or won't or don't want to step away from relational data warehouses. If, for example, some unique features of relational data warehouses, like very fast, simple queries or row-level security or things like that, if they are critical and the company cannot avoid using that. Data fabric can be used if a client is not afraid of vendor lock, because with modern data warehouse, it is possible to change different components of the system to different vendors. You can go from one database engine to the other. You can go from one parallel processing platform to the other. If you go with data fabric, usually it's a one single product. And if you select it, you stuck with it for a very long time. Changing it, which would mean changing everything in your project. It would be huge. Data Lakehouse is very much the default these days, and you can use it if there are no good reasons not to use it. Sometimes, in some cases, data lakehouse might not be the best solution if you still need relational component, or if you really need data mesh because your client is so big and so massive that a regular data lakehouse won't really do the job. But in most cases, data lakehouse will just work. It is the new standard, I would say. And data mesh is for very large companies who tried everything and nothing worked, and they desperate. Then you can say data mesh. It will be painful, but it might help. Most companies, though, will use pieces of each architecture to build a solution, not pure form of one of the approaches that we discussed. Sometimes there is a little bit of data lakehouse, and in some other part of the company there is a relational data warehouse, and someone might try to implement a little piece of data mesh just for a part of their infrastructure to see if it works. Those kind of hybrid solutions are very common, but of course it is better and easier to choose one approach and stick with it. Yes, demo time. And for the demo, we will be using the Delta Lake approach because it is very popular, it's the new norm. So let's look at in details what it looks like. And Delta Lake consists of two components, the storage and the processing engine. Here you can see a Microsoft Azure Cloud interface, and it has its own processing storage for Delta Lake called Synapse Analytics, but we will not be using it today. Every big cloud provider has their own version of the Delta Lake processing, but there are a few third-party providers. The two big companies are Databricks and Snowflake, and today we're going to use Databricks. So let's begin by creating the new instance of the Databricks in Azure. Databricks is available in all major cloud providers. It's exactly the same Databricks everywhere in all three of them. And for the demo, let's select the trial pricing tier. If you want to play around with Databricks, this 14 days trial is available on all platforms, I believe. So you can use it to play around without actually paying. I think it will still charge you for the cluster that you use, but you can use a small cluster and turn it off after you've done, so the cost will be still pretty small. All the settings we will leave at default, and create Databricks. We will need a storage too, so while did it start? Did you start? Oh, validating. Validating succeeded. And create, and it started the deployment. While it is doing the deployment, we will also need a data storage. And for data storage, in this case, we will use the Azure storage account. In every cloud provider, the storage has a different name. In Amazon, it's S3 bucket, I think. And in Google, it's something else. In Azure, it's just a storage account. Let's call it Scitech demo. And one important it offers us different options for redundancy, depending on what disaster we want to be protected from. Local redundant storage means that if one physical server goes down, then on different machine in the same data center, our data will be duplicated. In case of other redundant options, the data will be duplicated in different data center in the same city or in the same state if it's in the United States, or in the same country or in different countries if we are worrying about some kind of global disasters, if the whole continent goes down, if there is a zombie apocalypse, we still want our reports available for the zombies. But in this case, we're going to use the cheapest option because it's a demo and we don't want to pay extra money. Very important in this case to put this check mark on a hierarchical namespace, because this is what makes Azure Storage Account a data lake storage generation 2. Without it, it's just a blob storage which cannot be used by Databricks. So if you're gonna do this, remember about this option. Everything else we are gonna leave by default. Start creating. Another another item that we need to create in Azure is called Databricks Access Controller. This is a middle layer between, access connector, not controller. It is a middle layer between Databricks and storage account, which works to provide security, to set up access, what kind of access Databricks has, and how is it going to use it. Why is it not part of the Databricks itself? Why do we need to create a separate resource for that in Azure? Because Databricks is exactly the same on all three cloud platforms. And Azure Storage Account is an Azure-specific resource. So in order to work with Azure-specific resource, we need an Azure-specific connector. So in other clouds, there are other connectors to work with local resources. We don't need East US, we need West Europe. Thank you very much. Let's call it Databricks demo access connector. View and create. So now we have, as soon as it finishes deployment, we have all components of the data lake. We have the processing engine, which is Databricks. We have the storage, which is the storage account. And we have the, sorry? Yes, thank you. So now let's do some setup. Let's give the Databricks an actual access to our storage account. And in order to do that, first thing we do is we go to the storage account access control, and we give the Databricks access controller a membership. In order to work with files stored in the storage account, it has to be a member of a role storage account. Second. Yes, it will be blob data contributor. You are correct. Storage blob data contributor, and we.
Actually, it has write access as well. I don't know whether it's lead.
No, I think data contributor has both write and read access. Review and assign. Review and assign. And now, if we go, let's open it in a different tab. If we go back to our Databricks and launch the workspace, we will be able to use this connector to connect to our storage. This is the Databricks web interface. It is the same if you use it in Amazon or Google, and it is going to change in near future. I've read some news from Databricks from last week that they are doing a major redesign of of their notebook interface and their interface in general. There is no specific dates yet, but there will be some big changes. But for now, what we need to do to connect from Databricks to the storage, we can go to the catalog, external data, and first we're going to create, this is something that was created automatically when we created the instance of Databricks, but we will need first create an external credential based on our access connector. So we provide the name, we provide resource ID.
It's like the secrets.
Uh,
No, I used to create the secrets inside the Databricks that is connected with like the keyboard. I mean,
yeah,
another kind of.
we will do that today a little bit later. So we created the storage credentials, and now when we can use it to actually create an external location. Before we create an external location, in our storage account, we need well, a container which will actually store the files, and then we can connect to that container from Databricks. I'm going to use the so-called medallion architecture, which means that the data is split into 3 layers: bronze, silver, and gold. The bronze layer is the raw data as is, as it comes from the source, unprocessed, with maybe wrong data types, with wrong column names, with everything wrong. The silver layer is when we have the correct types, when we have the descriptive names, when we separate, for example, JSON columns into separate columns with individual values. And the gold layer is pre-aggregated data prepared for reports, when we have some kind of reports that want pre-calculated totals or something like that. That would be the gold. So let's begin with bronze. Yes, I think that's correct. Bronze. Silver.
You're also going to move data from bronze to silver and then
Gold.
to go to transformation, right?
Sorry?
So you also will do in the future data transformation from bronze to silver, from silver to gold.
Yes, yes, that's right. And one more container we are going to create, which, one second, yes, which will be called checkpoint. And it will be an intermediate storage for streaming data, because we were going to work with streaming data to make things interesting. And for that, we will need an intermediate checkpoint storage, which will be this. And now,
The small type of checkpoint. No, you wrote checkpoint.
yes, oops, sorry. Yeah, you're right. Let's delete this one and create the correct one. Checkpoint. And then in the Databricks, in the external locations, we say create location. And here, unfortunately, we have to type a lot of things by hand. It's not an automated process. Of course, in a real production environment, you wouldn't do it through UI at all. Everything will be some kind of Terraform script. And then you won't have this problem. But right now, we select the credential. We know that this credential has access to the storage, and we need to provide a URL of the storage. This is on, right?
And the protocol is correct with double S?
Yes, it is with double S. Create. Well, we will know in a second. Test connection. Yes, no typos. And then we need to repeat this operation 3 more times. Uh, yes, it's an internal protocol used by Azure Cloud. Yeah, so let's just do some copy pasting. Silver instead of bronze.
Yeah, I just see it for the first time before.
Yeah, maybe it's I know it's DB is against TCP.
DDP.
And,
Might be a press. The last one you wanted.
Alt. Okay. And one more checkpoint. So now we have access to these external locations from Databricks. So if we want, we can build an ETL pipeline that will upload some kind of files to this storage, and then we can use Databricks Notebook to process those files. But we will do something different. I think something more interesting. We're going to work with streaming data as a data source. And for a source of streaming data, we are going to use Azure Event Hub. So let's create instance of Event Hub. Azure Event Hub is pretty similar to things like Kafka. Maybe you've worked with them. It is an event processing engine that can process a huge amount of events without losing the correct order of events and guaranteeing its delivery. And so let's call it something simple. Standard pricing tier. Yes. The premium is 750 per PU per month. I don't really remember what's the difference between standard and premium. There are some additional features, but
The difference is quite significant.
never worked with premium, so I hope it's something valuable. We are gonna use it, and while we're waiting, it is now time to create a compute cluster in Databricks, because usually it is the longest operation during the deployment. So let's better start it early. Let's select maybe a small cluster, 1 to 4 workers. Don't need anything crazy. Create compute. And since we want to work with Event Hub, we will need to add to our compute a library to actually access the Event Hub, because it does not have support for Event Hub by default. It has support for Kafka by default, but not Azure Event Hub. There is, of course, a library that allows us to use Event Hub in very similar way as Kafka, the same syntax, just different option. Okay, so the reason, since I already did this when preparing for this presentation, the Google Chrome offers me an autocomplete. This is the name of the library, Azure Event Hubs Spark. We can check if this is the latest version. Unfortunately, the search of the packages here is pretty limited, so you have to use the normal search to find the libraries that you want, and this is the library that we are going to use, Azure Event Hub Spark. The latest version is 2.12, package version 2.3.22. I think this is exactly the one that we are using. Yes. Click install. This will take some time while it's running. How exactly the Databricks is going to access Event Hub? When we want to access Event Hub, actually it's Event Hub's namespace. We need to create a instance of Event Hub. So let's go to Hubs. Yes, here. And we create Event Hub instance. We call it that we used last time, Event Hub. Very simple. And for access, we are going to use an shared access key. By default, the Event Hub has this root managed shared access key with a lot of permissions. We don't really want to give Databricks so many permissions because the best practice is to give as few permissions as possible for every part of the system. So we're just going to create a new SAS policy which can only listen but not send or manage events. Let's call it listener SAS. And as soon as it's created, we can go and take connection string from it. And connection string includes some sensitive information. It includes the key. And we don't want, of course, to hard code this information. And the best way to deal with this kind of sensitive information is to store it inside of Azure Key Vault. So let's create a Key Vault. And then we will access this Key Vault from inside the Databricks. We will extract this connection string, and we will use it to connect to the Event Hub. West Europe, thank you very much. Let's call it. Right, because I created it already when I was preparing, and since it's using soft delete, it won't allow me to create Key Vault with the same exact name again for, yeah, so I just do it like this. And important thing that you need to do with Key Vault, if you want to access it from inside the Databricks, is to change permission model to Vault Access Policy. The Azure role-based access control is better, it's more modern, but it's not yet supported by the Databricks, so we have to go with this. All the other settings, we can leave to default. Just wait a few seconds. Usually key vault is pretty fast to deploy because it's a small thing. And in the list of secrets, we're creating a new secret. And let's call it event hub connection string. And paste the key, the connection string from the event hub. Create, done. Now we need to access this key vault from inside Databricks. So we go to our data. What is this? Quota exceeded. Right. Because I already created instance of Databricks when I was preparing, and it has a pretty low quota for virtual cores. Let's try. Okay, this one we can just destroy. Let's try create a very small compute with just one worker node and not use photon acceleration. And sorry? Say it again?
They use Linux.
Yes. Photon acceleration is something that Databricks created. It is their version of Spark engine. So basic Spark engine is open source, but Databricks created a better version of it. They called it Photon, and it is really faster than regular Spark. But it is, of course, cost some additional money to use. And let's select just the smallest sized worker that we can. This is 8 gigabytes memory, one worker. Should be fine. I hope. And yeah, library. Sorry for this small issue. And going back to previous question, how are we gonna access the key vault from the Databricks instance? For that, we are gonna use something called a secret scope in Databricks. And there is a very interesting way to do it. There is no UI button or anything. We will have to just write a specific URL. And if you don't know this URL or don't read about it in documentation, there is no way to guess from the UI. I don't know why they decided to do it like this. Pretty much, yes. And on. Databricks, what are you doing? Oh, because it's secrets. Yes. Now we're here. So we can create a secret scope based on the Azure Key Vault. Let's go to our Azure Key Vault. And somewhere in the properties, it will give us the URI, which we can copy and paste here, and the resource ID. This is how you create a Databricks secret scope that can go to Azure Key Vault and extract secrets from there. So you can safely store all sorts of passwords and other sensitive information without hard coding it. It is surprisingly not obvious. I've seen a lot of tutorials on the internet where connection strings and passwords are just plain text in Python notebooks, and that is, of course, unacceptable. Don't do that. Give me a second. Yes. Create. So yes, we have created key vault secret. The compute still created, but at least it didn't give us any errors yet. So now we have pretty much all the infrastructures that we need. We have the storage, we have the processing engine, we have the source, which is the stream of events. Let's do something. We need to write some code, or rather, since writing code would take too much time and we don't have all the time in the world, we are going to use GitHub to get some code that I've already written for this specific purpose. Yes, it's already suggested. So it's from my personal store GitHub. Sorry? No, it's Python and SQL. You will see in a second. Databricks does not support Java. Might be incomplete. Why?
Container is still creating.
Right. Interesting. Okay, let's wait till it's done. But what we are going to do is we are going to use a notebook in Python and SQL to access the event data from Event Hub, to stream it, process it, and save it in different versions in all three layers of our model. The raw data as is will be saved as bronze, the cleaned up will be silver, and then aggregated will go to gold. Where are we going to get these events? We don't want to create an application that will generate events, of course, but fortunately for us, Event Hub has this nice feature. If you open it, called generating test data. It's relatively new, and we can just tell Event Hub, please give us a sample data set. It has several data sets available. We're going to use the one called Yellow Taxi. It imitates an application working with taxi, with all sorts of data from taxi drivers. If you send sound, it will just send some events, 50 events, into this Event Hub. No one is listening right now, so it just went into the void. But later we will do the same when Databricks is listening in, and it will be processing them. Ready yet? Oh yeah, success. Let's try again to create a repo. Oh, wait, what is this? Did it? It did clone the repo. It just was the error anyway. Thank you, Databricks. Right, so let's begin with the first notebook. This one is written in SQL. We can select between four languages when we work with Databricks: Python, SQL, Scala, and R. The most popular are Python and SQL. I've never seen R used in Databricks at all. Scala sometimes, rarely, because some data scientists are more familiar with Scala than Python. But mostly it's SQL and Python. In this case, it's SQL. And the first operation we do is we create these virtual relational metadata layers for bronze, silver, and gold data. Create schema is the alternative to create database in the relational database. So we are creating three virtual databases for bronze, silver, and gold data on the storages that we just created. Databricks has its own built-in storage that is generated when we create an instance of Databricks, but in this case we're not going to use it. We're going to use the external storage that we created earlier. So we select a cluster, we say run all of our code cells. So first cell creates these databases, and the others are creating tables. And in this case, table means a delta file with a layer of metadata on top of it. It will be an empty file, just the structure. So we say create table, provide the structure, and then this is very important part, using delta. It means that in behind the scenes, it will actually be a delta file. One for the bronze layer, one for the silver layer, and one for the gold layer. And since our cluster consists of just one node, it's not very fast. Let's wait until it's done. So the bronze one is complete, silver complete.
It's faster than our computer. And it was creating tables much faster.
And gold. All done. And the last cell I used for debugging to delete some intermediate data. Right now all tables are empty, so number of affected rows, 0. Thank you. So now we have these three tables in our storage. Let's do something with them. In this notebook, we are going to use Python and Scala to connect to our Event Hub. Here we are connecting to Event Hub using the connection string stored in the key vault. You see how we are using the secret scope that we created earlier. This is a pointer to Azure Key Vault. We extract the connection string from it. We connect using the read stream operation. So it is a structure, the technology, this approach is called structured streaming, and we start listening to stream of events. If we run this code, you will see in a second that this first cell will finish working after all the connectors are successfully created and initialized, but the second cell and everything after it, they will keep running because they're listening to stream and they will be listening forever until stopped, interrupted, or if something breaks. That way, we can build pipeline that will process data as it comes in real time, and it will become available to the consumers in real time, except unless something happens. This does not exist. Timeout. Interesting. You rehearse this thing, it works well, and then you go in front of people and everything explodes. Let's try this again. Maybe it's just some kind of networking issue. System does not exist. Connection string. No, connection string was copied as is from the event hub, so it can't be incorrect. Also, it shows here the sensitive information. Thank you, Databricks. That's not what I wanted.
You had a different name for the keyboard. Maybe that's it.
No, this is shared access.
Let's
Keyboard 1 or something.
key vault. No, this is not the name of the key vault. This is the name of a secret scope. And the secret scope was called exactly like this, key vault secret. And the secret is called event hub connection string. Otherwise, it wouldn't be able to read this from the key vault. So this part works. Did event hub name Cytec demo event hub? Cytec demo event hub. Oops. No. 1 second, please. It's not yet working with the storage.
No, it receives the key from the key vault. It cannot connect to the storage itself.
Where do you specify the file system?
That's the fun part. Here we're not trying to save anything yet. It's just a data frame that is loaded from Event Hub as is without even touching the storage. We will work with storage later.
But the name is different. Gen 2.
Sorry, can you repeat that again?
This name here is kind of incorrect. This one.
Okay. Because probably it is using its own internal storage as a checkpoint. Right, because I forgot to specify a checkpoint.
Oh.
Did I? Guess so.
Maybe it's because it cloned repo when the storage was not created, so this connection to the storage does not really exist. So we need to provide a block.
I don't think that's the case. Anyway, let me just, I was hoping to show you this in the process, but let me just explain what the code, let me try it again maybe one time. It didn't work, and the second it will. No. Let me just explain what was supposed to happen. So what was supposed to be happening is that we would create this data frame that reads the stream from Event Hub. And in the next step, when we do display of this data frame, it would be empty because we have no events in the Event Hub currently. But then as soon as we go to the Event Hub and generate some more sample events, then immediately or almost immediately within a few seconds, we will see here a table with an actual rows of data from Event Hub. The raw data where the JSON generated would be encoded as a row of unreadable garbage. And like instead of this JSON, that would be just a lot of random letters. So in the next cells, we take this data frame and we start to extract something valuable from it. Select a column called body, which is an actual encoded JSON. Then apply a schema, because we know the schema of the data. Apply the schema and extract columns from this JSON. There is a way to automatically detect schema without applying it like this. But it is a little bit, it requires some additional code, and it's beyond the scope of this presentation. And then when we have these columns extracted from JSON, we would save them into the bronze layer table. This is still the raw data. If we look at the source, you will notice that date time are in Unix time format, which is not human readable. So this is the raw data, which we cannot use immediately. So it's a bronze layer. We save it into the bronze layer to, yes, here checkpoint is specified. We are saving it to the bronze layer storage as a delta format in the append mode, which means that every time when new event comes in through the Event Hub, new record is added to the existing table, existing file. It's not overwritten. Instead, it is appended with the new data. And then in our pipeline, we go from bronze to the silver layer, and we no longer use Event Hub as a source. From this point on, we read the stream from bronze layer. This part of pipeline from bronze to silver, it doesn't know anything about Event Hub. It doesn't have to know. It just operates between two steps. We take data from bronze. We convert the date time from Unix to the normal timestamp format. There are also some additional modifications. We add the current timestamp as an additional column. And so this is a clean data, which we can already use in our reports, in our analysis. So we save it again as a stream to the silver layer. And then we do something similar, going from the silver to the gold layer. We do grouping, we do aggregating, calculating total, with one small but important difference. The output mode, instead of append, we use complete every time when we get new events. The final gold layer table is entirely overwritten because the aggregated values change. So the old ones wouldn't make any sense anymore. And this pipeline, it can run indefinitely. We can start it and just keep it running, or we can put it on pause and then start it at some point, and it will get the backlog of events that went through Event Hub while it was on pause. This allows us to integrate real-time data into our Lake warehouse. So the end users, the reporting systems, will immediately see what just happened, the most recent sales or most recent events from the IoT devices. They don't have to wait for the nightly recalculation. The data is right there at their fingertips. Of course, this approach has one downside. You will have to keep a compute running 24/7, and that's expensive. They are billed by a minute, and if you forget to turn off your cluster before the weekend, then on Monday you will see a surprising bill. Don't do that. Telling from experience.
Can you create a schedule to run it and start it on schedule?
Yes. I'm not sure if you can create a schedule inside of Databricks itself, but you can create a schedule in Azure Data Factory, and it has one of the components is called Run Databricks Notebook. So you can add this notebook in as a step of Data Factory and put it under schedule, and it will run when you want. Just don't forget then to add a step to turn off the compute because it has this option to automatically turn off, but I think 120 minutes is the lowest allowed value. You can't set it to turn off after 5 minutes of an activity. It just won't let you.
This is good choice. You pay for Azure Data Factory.
Which
with the
activity?
schedule Databricks, and you pay completely just for Databricks.
Yeah.
Sorry, what was the question?
What an activity does it mean?
In-
An activity, if there are no events?
No, in activity if there are no running notebooks. If there are no events but our notebooks is still running, it's not in activity according to this logic. So if we keep this notebook running, even when there is no events ever, it will still be billing 24/7.
It's expensive, right?
Yes, that is, the cost is one of the biggest problems of Databricks. It's an expensive system, especially if you run it for the real-time tasks. If you use it for processing, when you activate cluster, spend, I don't know, 20 minutes to process all your data that is stored in data storage and then turn it off again, then it won't be too expensive. But the longer it runs, the worse it gets.
Charge something on top of the cloud provider charge. So for cluster computing, you pay for Azure or AWS, but Databricks charge on top of that.
They have a very confusing pricing policy. There are different offers. There are different default offers. And then there is the whole world of custom contracts when you call the representative and say, I am from company this and that, and we want to sign a contract. Let's discuss a special terms just for us. Because most people does that. Microsoft is heavily pushing the idea that the best cost you will get if you call them directly. So it doesn't really make sense to try to build a strategy on their public pricing. You just need to call them or write them or send them your sales representative.
Again, we do call CPU, it's Databricks usage.
It's a unit of something. It's not really a physical, measurable value. I don't know why they chose this approach, because you can't say that this type of cluster with like 32 gigabytes of memory is this much DBU. It does not directly translate.
There's a difference between premium and standard, you can see.
Yes, but there is one thing that they don't want to say loudly, but in the last few months, there's been a lot of talks on around Databricks from people who has some inside information that they're gonna abandon standard at all. They will go only the premium tier, because premium tier includes the new model of security, the new model of metadata that they developed, and they pushing it hard, and they don't really want to deal with the old legacy approach, which is part of the standard tier. So they, in the near future, they will probably say it out loud, and we will all read in the news that Databricks is abandoning standard tier. So keep in mind that this will probably happen.
If you open the cluster you created, you can see how much DBUs it's using on top right corner.
And what do you
Oh, yeah, you're right. Sorry, I didn't know that. Interesting. So this
If you will see how this DBU session
I'm surprised.
won't allow me to change it. It's already stopped. Oh, edit, yes, right. Let's say 8 workers from 2 to 8. Or 1 to 5 DBU. So on 8 workers, it would be 5 DBU. And if we change worker type to, let's say, 16 gigabytes RAM, 2 to 9 DBU per hour. Yes. Yes. On my previous job, when we were using Databricks for batch processing, I think the heaviest processing that we had took around 7 minutes. Previously, when the same kind of processing was running inside of SQL Server by just the database engine, it was around 4 hours. So it is really fast, but not cheap. Well, in the SQL Server, it was a storage procedure written in SQL, and in Databricks, it was written in Python. So maybe there was also a factor of better code. Who knows? But the difference is still there. One interesting way to try and save money with Databricks is this checkbox spot instances. If you do that, then Databricks will not create a dedicated dedicated instances for your cluster. It would rather try and grab whatever is available and was created for someone else in the cloud. But as soon as someone else wants a cluster of the same type, it will take those instances from you, and your work in progress will be interrupted. So if you're ready for this kind of risk, it's not often. I've read statistics, I think it's less than 10% of jobs gets interrupted, but spot instances are much cheaper than normal because of they're not reliable.
That will work, I can assume, for short and quick
Yes,
things. So
exactly. If you have a short tasks that you know will not suffer from interruptions, you can go with stop-out instances. If you have something that will run for 3 hours, it's pretty high chance that it will be interrupted. So maybe rethink your priorities. Something that runs for 3 hours in Databricks probably could use optimization. So that was my demo. And if you have questions, there is one last slide in my slides. Yes, questions.